Okay, today I'm going to talk about machine learning and ADS-CFT. And this is quite similar what we heard from Professor Rak-Kyeong Ken yesterday. But I prepared this for researchers today. So, okay. Oops. Oh, okay. So let me introduce myself. I'm Daichi Takeda, and I recently took my PhD, and now I am doing first postdoc in RIKEN iTHEMS in Japan. So my what I did so far is because I'm still a baby researcher, I can list up all the papers, and my field is like this. I first did string field theory, which is quantum field theory version of string theory, and after that I changed my field to the ADS-CFT field, like this bulk reconstruction program, which I'm going to explain from now on. And today's topic is so related to the bulk reconstruction program, and also the ADS-CMT stuff. I also applied the ADS-CFT to the black hole thermodynamics and in this series of work. And the most recent paper is about how to apply ADS-CFT correspondence to open quantum system, like when the quantum field theory is open, how to modify the dictionary of the ADS-CFT correspondence. So this is what I have done so far in my research activity. So today's topic is about this, this number 9, with Professor Hashimoto and Koshiro Matsuo and Mura-san, Ogiwara-san. And Koji Hashimoto is my PhD advisor, was my PhD advisor, and those 3 people are in the field of machine learning. So we did physics. I did physics with Hashimoto-san, and the other one helped us implementing machine learning architecture, and we did together. So before moving on to the main topic, I'd like to explain my dream. The motivation of my research is doing quantum gravity experiments in laboratories. So in what sense? We have this kind of phase diagram for specific materials, and we call this point quantum critical point. And quantum critical point is known to be described by conformal field theory. Conformal field theory is a scale invariant theory at 0 temperature exactly. Then it can be modified toward higher temperature region. So, and the ADS-CFT duality, if we believe that this duality is valid for the for various conformal field theories, then we expect that this point, quantum critical point, and around that point can be also described by a gravity theory. And in most cases, we assume that gravity is classical because the classical gravity is very useful, and we can calculate many things. When the conformal field theory is strongly correlated and the degrees of freedom of the theory is very high, then in that case, we can use classical gravity and perturbative theory. But even for that parameter region, we can expect that some quantum gravity appears for that theory. Like it is known that if we lower the temperature, then in the higher temperature phase, we have black hole, but it goes to disappear and evaporates. In that case, because black hole is known to have singularity, and which is related to quantum gravity effect. So we can get some quantum gravity effect on the boundary. So this is a kind of my dream. I want to find a conformal field theory in the laboratory setup, and I want to find the dual gravity theory. Then we can do this kind of experiment and find some signal of quantum gravity in the laboratory. This is my motivation. So to do that, we need to find a phenomenological ADS theory, which explains at least some features around the equilibrium states of quantum material in terms of gravity. So here I'm writing, so for example, we have 4-point correlation functions in quantum field theory side, I mean material side. Then so this data can, in principle, be obtained by using conformal field theory. But according to the GKPW dictionary, which is the most basic dictionary in ADS-CFT, we can also calculate the same quantity by just perturbatively calculating classical field theory in the bulk on the fixed background. So yes, I want to find classical gravitational theory, which is dual to material. But before doing so, as I write here, that those quantities can be calculated on the fixed background, we first have to identify what is the metric corresponding to a given CFT state. I mean, this equilibrium states. So this is the main goal of this talk. Then we use boundary linear response, material linear response theory to bulk metric. I'll explain what is linear response theory. So linear response theory is equivalent, linear response data is equivalent to the retarded Green function. I mean, if you add some source, how it propagates over the material. That's the meaning of linear response. So we slightly perturb Hamiltonian like this because we are considering field theory. I put the arguments of the space. So so-called interaction picture quantum time evolution of the quantum theory can be written like this. So how we can get this state is we just solve the Schrödinger equation, then we can obtain this simple time evolution. Here, add means adjoint operation. So as I explained, in this talk, we always assume that the initial state is the Gibbs state, I mean thermal equilibrium state. So in linear response theory, we assume that this source J is very small. So we can expand the 1-point correlation function in this way. We just expand with respect to J, meaning that expansion with respect to V. So in this case, to the first order of J, we obtain this formula. We just expand this, then you can find this formula easily. And this is what we call the retarded Green's function. And this second term, the whole second term is called the linear response because this part is linear to the source. So for simplicity, we assume that we choose the operator or material so that this part vanishes. And hereafter, we assume that. So I explained what is linear response, and in this slide, I'll explain how to use the linear response to reconstruct the dual series background metric. So first, we prepare ring-shaped material in given state here. So in this talk, I assume that the material is ring-shaped. We just process the material into ring shape for simplicity. So in this case, the material dimension is 1 plus time, so two-dimensional conformal field series. And we do some experiments, or if we have some Hamiltonian model, we can do numerical experiments and get linear response data, adding source and get the linear response. Then we find the bulk metric that reproduces those data as an input of the boundary condition of this gravitational theory. Here, machine learning comes in. So this is kind of summary of my talk. And in more a bit detail, the summary of this talk is like this. Why the ring shape is important? It's in principle not important. I mean to implement this machine learning architecture, it is simple. So so we need to use the not only S wave, but also P wave or higher waves. So in that case, so if the dimension is higher, we have many other angular momentum modes. So it's very complicated. So as a first step, I want to use ring-shaped material so that we can easily construct the machine learning architecture. So this is a summary. We first prepare Gibbs state and do linear response theory. In this theory side, we just solve Schrödinger equation. This is what we call von Neumann equation, but you can think that this is equivalent to Schrödinger equation. So in the dual theory side, classical theory side, we just solve the equation of motion. And particularly, if we choose this operator O as a scalar, then we just use classical scalar theory and free scalar theory in the bulk theory. So this, we then to implement machine learning architecture, then we just discretize this equation of motion in this way with the boundary condition of J and O. So in the bulk theory, as I will explain later, those data can be understood as input. I mean, the boundary condition of at the boundary. Then we solve the equation of motion toward deep into the bulk. And finally, we put some physical boundary condition at C equals 0. Okay, so this is my the summary of this talk. The item of this talk. First, I explain the forward problem in more detail. The how to calculate the boundary data, the linear response boundary data from the bulk theory. And second, I formulate what is the inverse problem in more detail. I mean, from the bulk metric to the boundary linear, from boundary linear response to the bulk unknown metric. Then we solve this inverse problem by using neural network. Then finally, I demonstrate whether this architecture works by using some forward problems. So I said in the future, I like to apply this to the real material data and find holographic material toward future quantum gravity experiments. But in my talk, I just use known bulk metric and check if this architecture reproduces the known result. So let us move on to the forward problem. So in ADS-CFT, what is the ADS-CFT? It means the theory, in both theories, the generating functionals are equal in this sense. So here I said large n. In the large n limit, this generating functional with source J coupled to operator O is equal to some on-shell evaluation of the action of the bulk gravitational theory with this boundary condition at the infinity. So large n means that the in the material side, the degrees of freedom is very large. More imprecise, the central charge is very large. So we suppose that we can get some material whose central charge is not so small, and the equivalence is explained in by this relation. So in the quantum theory side, if you add some source here, the source here, then it of course propagates on the boundary. But in the gravity side, it works as an boundary conditions and it propagates inside. The wave dives into the extra dimension. And those two calculations are equal. That's what this dictionary means. So what is the bulk configuration? Bulk metric, which is dual to Gibbs state, the thermal equilibrium state. Here, as I explained in the previous page, we just apply the dictionary, the equivalence between two path integral in Euclidean signature. So thermal equilibrium state is the partition function of that can be written the trace over exponential to the minus beta h. Then this is it is known that this trace can be expressed by path integral over Euclidean manifold. Then by using the ADS-CFT dictionary, this can be just be expressed by the classical action of gravitational theory. And in this case, because we are not putting any source, the boundary condition of fields except metric is just like this. It has to vanishes at the boundary. So as a demonstration, I'd like to explain a case of if the bulk theory is Einstein theory. In that case, it is known that we find two solutions. One is the black hole spacetime, which is called Schwarzschild ADS, and the other one is pure ADS spacetime. So nothing is inside, but on the other hand, the other one has a black hole. And there is a phase transition between two spacetimes. In the high temperature phase, this solution is favored. And the lower temperature phase, this solution is favored. So how to check this is that because this on-shell evaluation is just an saddle point approximation of path integral over all the possible configuration of the bulk, we we have to find all the possible solutions to approximate the path integral, and we compare which one dominates the contribution of this. Then in the high temperature phase, this is favored, and low temperature phase, this pure ADS is favored. So this is Hawking page transition. So yes, summary ADS. Okay. But in general series, I mean non-Einstein series, we do not know if the bulk has a black hole. But at least because we prepare ring-shaped material in my talk, and the state is thermal equilibrium, then we can assume that in the dual theory, the metric is static and spherically symmetric. But we cannot assume that if there is a black hole.
About the finite temperature system, in the beginning of your talk, you said that it's carefully is characterized CFT.
Yes.
Varying the this state, but you know about finite temperature. Okay, so you believe that your equation can be applied to the quantum critical region or
Yes, quantum critical region and also some higher temperature phase. And we can deform the conformal field theory by adding one scale temperature. And we know that it works in ADS-CFT correspondence.
how about outside of
I think if the deformation is not so drastic, we can deform the bulk field theory. And I think in that case, the ADS-CFT still works. So, okay. Okay. So I explained how we can find the dual bulk metric, which is dual to the thermal equilibrium state. So because I said I use linear response data to reconstruct the bulk. Sorry, we are now doing the forward problem, so I have to explain how to calculate linear response data by using gravitational theory. In this paper, it is known that the Schwinger-Keldysh formalism, which can calculate thermal correlators, can also be explained from the bulk theory, like this complex contour in the bulk theory. But this is too tough to do. But fortunately, for linear response theory, this complex manifold problem reduces to as follows. So we just calculate this equation of motion, the free equation of motion, and but with by imposing this boundary condition at infinity. Infinity corresponds to the boundary. And when we are interested in up to order J, then we just need free theory. I mean, if you have potential, you can, of course, consider that this bulk theory has a potential. But in most cases, it can be expanded like cubic term, quadratic force term, like that. Then if the boundary source J is small, the excitation of the bulk field is also small, so we can ignore that term. So in this case, we just have to consider free theory on the fixed background because the J is small. So this metric J is the one dual to the Gibbs state. And I mean, this metric G is what we determined in the previous slide. So For summary, no, yeah, sorry. So linear response around gives state. To do that, not only this boundary condition, but also we have to impose this boundary condition inside the box. I mean, because we're doing causal setup, then the initial configuration must be the same as the equilibrium state. So nothing is excited in the bulk. That's the boundary condition. And I call this as a retarded boundary condition. And if the black hole exists inside the bulk, this boundary condition can be understood as ingoing boundary condition because it causally propagates toward future. So if source J is turned off at the past, in that case, this is automatically satisfied. So ingoing boundary condition can reproduce this boundary condition. But if there is no black hole, then the boundary condition changes. So typically, the bulk field, the two linearly independent solution of the equation of motion behaves like this. The one blows up and the one goes to zero smoothly. So this blowing up solution is not physical, so we have to ignore that. So the boundary condition is that we have to choose the regular one. And of course, to satisfy this boundary condition, this is technical, so I don't explain in this talk, but we have to do some I-epsilon trick. Anyway, this retarded boundary condition can be rephrased in other words like this, depending on whether the black hole exists or not. So by solving the equation of motion with those boundary conditions, how we can get the linear response data of the boundary? This is easy. We just expand the solution and see this part. So the subleading part. Then we can get the linear response data. This is the forward process. So I summarize the forward problem. So we first do this calculation and find the dual metric by using the GKPW dictionary. Then by using this thermal metric, we solve the free scalar theory with boundary condition J, and also retarded boundary condition inside the bulk. Then we can get the solution phi. Then we expand the phi like this. Then the subleading part gives us the linear response data. This is forward problem. So let's move on to the inverse problem.
So you have a localized perturbation, then the solution can be only function of R, or it can be function of the angle.
It can be the function of angular.
Yeah, in general.
Yeah, in general. No, I just didn't write it explicitly.
But in general, there should be a degree.
Yeah, and actually we use the angular dependence. The inverse problem. So what is the inverse problem in this case? In short, we first prepare ring-shaped material in Gibbs state and get the linear response data by experimental simulation, something like that. Here, I further assume that for simplicity, O is a scalar primary operator. Then find a bulk metric that reproduces the data. So first, we put the ansatz on the metric. What is the ansatz? Static and spherically symmetric. So because we prepare thermal equilibrium state and we prepare ring-shaped material, then we can also assume that the bulk metric is static and spherically symmetric. In this case, in general, the metric can be written like this. So there's only the all dependence for each component, but we still have residual gauge, the transformation of all coordinate. So by using this residual gauge, we gauge fix like this, where G without any index is the determinant of the metric. So we gauge fix like this. And we can also set the coordinates xi runs from 0 to 1. So there are two independent components, GTT and G theta theta. But as we will see later, in the machine learning architecture, this combination appeared. So we regard the large xi and large theta as the two independent components of the metric. So by recovering this psi and theta, we can get the true metric. So we consider properly scale field as the bulk theory. We have the data of linear response under this perturbation on the boundary theory. Here, always scalar primary with scale dimension delta, and J is external source. Then in this case, in the bulk theory, we can expect that, as I explained, that the bulk theory is free on a fixed background because we just need small j. And additionally, if the scale dimension of scalar operator is delta, it is known that the bulk field theory's mass is given by this like this relation. Now, the difference between the forward process and the back inverse problem is that in the inverse problem, we use the data J and O as the boundary condition of the bulk equation of motion. In the forward problem, we just use J and some physical boundary condition inside the bulk. Then we get this operator's expectation value. But in this case, we use those two boundary data, and we need to find the unknown metric G.
So I'm confused. You are going to use the spherically symmetric ansatz
To the metric.
The configuration is not spherically symmetric because you have a localized perturbation. Then how your ansatz corresponds to this figure?
So the source can be dependent on the angular coordinate, but the bulk metric is because we fix the bulk metric, we only consider the probe approximation. So the bulk.
I see. The background is
yeah.
perturbation.
Yes.
Then perturbation solution itself should be independent.
Yes.
Okay. Now I understand.
Thank you. Thank you for asking. Sorry? Free what? Composition. Yes. Fourier, yeah. We are going to use Fourier decomposition later. So below, for simplicity, we consider the massless case. But the generalization is very simple. So in that case, we consider massless free scalar field. So yeah, like like you asked, we go to the Fourier space. So we expand the field like this. Here, I just extract one Fourier component. Then the equation of motion can be written like this. Here, the vector z has two components, and second order differential equation can be reformulated as the first order differential equation by using this z. And the unknown metric components appear in this matrix. And also at c equals 0, at the deep inside the bulk, the z must satisfy the retarded boundary condition. So here is a summary of the inverse problem, the bulk metric from boundary linear response. This is what I showed in the introduction. So we have this data, and we find unknown metric by solving differential equation, and we use omega k and the Fourier components of linear response data as the input of the boundary condition and the input of the differential equation, and we discretize it. Then the metric components appear as the weights. Okay. Then finally, at c equals 0, we impose retarded boundary condition. So how to solve this problem with machine learning? This is what we do as summary. I first show the simplest version of how to do machine learning. But later, I refine this architecture. Our architecture is drawn like this. This direction is the Z direction, and this is the bulk inside the bulk. This is the boundary. So we input the two components of Z, then and also omega and K. Then okay. We pass this data to the bulk. And we also prepare false boundary data. I mean, the false data doesn't satisfy good boundary condition in the bulk. So we prepare true data and false data and do the binary classification.
Sorry, can you repeat once?
Z1 is the bulk field phi, and Z2 is phi prime. Yeah.
Okay.
Sorry? It's all said.
When you read all, then see what it's into.
Yes. Yes. K? Yes, in this case, K is quantized. Total dimension of the boundary theory. The 2 plus 1. Yeah. Spherical asymmetry.
Because we only have X symmetry and planar and hyperbolic here.
Yeah.
And what is the role of the really shaped material?
But yeah, this one is discretized, but it doesn't change the problem so drastically. But the problem is that in the real setup, we cannot prepare a very long material, so it's convenient if it's compact.
I understand it doing post of the period of boundary.
Yes. So, and finally, in the final layer, we ask if the output matches the boundary condition. But we don't know if there is black hole or not. So we also introduce some weight parameter rho, and I explain later. So in the bulk layer, this part, we just discretize the equation of motion, and the architecture of this is like this. The input is Z1, Z2, omega k. And first we just multiply the weight, I mean the unknown metric to Z1, and we get two output, and also this part can be obtained like this. And we just pass through omega and k. Then we put activation part here, and F maps the 6 components into this, like this. And this two line corresponds to X, this first 2 components. And we just pass through omega squared and k squared as it is. And this complex part just expresses this part. Then finally, in the boundary condition layer, I'll explain boundary condition layer. The typical behavior of the bulk field near xi equals 0 is given like this. If there is black hole, we put in going boundary condition, and the field phi behaves like this. And if there's no black hole, we put regular boundary condition, and in that case, the field behaves like this. So to check whether those boundary conditions are satisfied, we consider this quantity O. Here, the CF is the cutoff inside the bulk, which is very close to 0. And epsilon is some cutoff to just avoid the divergence. And here, rho is the parameter to be optimized. And in the case of black hole, B equals 0. And in the case of non-black hole, A equals 0. So we optimize these 2 parameters and also learn whether there is a horizon or not. So always expect to be very small. I mean, if the boundary condition is satisfied, this part vanishes. So always small for true data. And we construct the loss function as this because we are doing the binary classification. We just use the Hilbert-Leiber divergence like this. And here the function t, okay, so the t data is that if the data is true, it is 0, and false, it is 1. And the function to is like this. We input O, and it returns this, like this curve. So if O is very small, if the boundary condition is satisfied, then it stays around 0. But if O is far from 0, it is like 1. So it is classified as false. Okay. So this graph is taken from this paper by Tanaka-san. And I heard that this function is invented by you. We are calling this as Tanaka function. So the binary classification, the summary is like this. So I explained all the parts, but there's a refined version, and we introduce Rungekut layer to implement to improve the performance. So I have to slightly skip this part. So Rungekut method is just the better numerical solver of the differential equation. We just do some difficult things to improve the numerical numerically solving the differential equation. So I just skip this layer. So this layer is can be made by combining the bulk layer, which I explained before. So the final figure is like this. Yeah. Oh, layer. Yeah. Oh, but the weight is unknown metric, so we cannot solve. Yeah. So the metric is the weight, and with respect to that unknown metric, we do Runge-Kut method. Okay, finally the demonstration. The forward problem on BTZ background spacetime. Oh, yeah, BTZ spacetime is just a 3D ADS black hole spacetime, which is a vacuum Einstein solution. And we can do the forward problem by solving the classical equation of motion, and we get this data. And we forget about the bulk metric, and we reproduce the bulk metric only from this data. Here, we put L and R horizon equals to 1. Then, before learning, our initial weight is given like this. Here, the orange line is the initial weight, and the green line is the true black hole line. And also, we set the bulk layer as the weight rho as this. So completely neutral. It can be, it is the mixed version of ingoing boundary condition and regular boundary condition. And after learning, we expect that this part completely vanishes. So, and we chose the ADS, pure ADS metric as the initial weight, because we can always expect that it is at least asymptotically ADS. So it is convenient to choose ADS metric as the initial weight. So after learning, we get this figure. So you may be disappointed this part. Near the horizon, the real solution oscillates hard, so the numerical behavior gets worse. So yeah, we have to improve in some way at this point. But we can see that horizon emerges in some sense, because this coefficient is very small, and the boundary condition is now purely ingoing boundary condition. So the machine learned that there is horizon inside the bound. And also metric is somehow reproduced.
Oh, sorry, I didn't get the last one.
Okay.
So how do I understand the horizon emergence?
Oh, okay. So while you're out, and I explained that. Okay. Boundary condition. So typically, if there is black hole, the field behaves like this, and if not, the field goes like this. So we introduce the quantity O like this, and this part vanishes if the boundary condition is satisfied. But we introduce the parameter rho, and if B is 0, this reproduces ingoing boundary condition, and if A is 0, this corresponds to the regular boundary condition. We also optimize the parameter A and B. Yes. Then okay, sorry. So after learning, we set the initial parameter like this, and after learning, it almost vanishes. Thank you very much. I have to finish, so this is the summary. Okay, thank you very much.